Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey will take us somewhere ancient, deeper than history, older than bones. We're going to drift through the 5 great mass extinctions of Earth, those moments when life itself teetered on the edge of nothing, and yet, somehow, returned. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the history of extinction. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. The idea of extinction is, in some ways, the ultimate bedtime story. It's both an ending and a beginning. A reminder that even the mightiest forms of life, the toothy, the towering, the radiant, can vanish without ceremony, leaving behind only a fossil or a void. And yet, life has never stayed gone for long. It withdraws, regroups, changes shape, and reappears in forms both familiar and strange. To understand extinction, then, is to understand something deeper about time, about adaptation, and about the fragile yet astonishing resilience of life. Let's begin by asking, what is a mass extinction? You might imagine extinction as a slow fading, like a candle sputtering out. And that's true for most species. The vast majority of extinctions happen quietly, gradually, almost politely. Scientists call this background extinction, the natural rate at which species disappear due to changing environments, competition, or bad evolutionary luck. It's the soft tide of loss that hums beneath the ongoing symphony of life. But a mass extinction is not a tide, it is a wave, sudden, massive, and global. In these moments, Earth loses at least 3/4 of its species in what is, geologically speaking, the blink of an eye. And it doesn't just lose individuals, it loses entire lineages. Whole ecosystems unravel, niches collapse. The ancient sea that once shimmered with trilobites might suddenly go still. The forest that buzzed with dragonflies might fall silent, and the sky that once darkened with reptilian wings might hang empty for a long time. There have been 5 of these great events. Each one changed the direction of life on Earth, and in between there were long periods of stability, times when life diversified, sprawled, grew extravagant. Times when ecosystems became intricate tapestries, with every thread carefully woven by evolution. But then, with a shift in climate or a burst of volcanic fury or a rock from space, everything would come undone. It's tempting to think of mass extinctions as stories of destruction, but they are also stories of reinvention. The end of one world has always made way for the birth of another. After the trilobites vanished, new kinds of fish began to dominate. After the great forests collapsed, tiny tetrapods crawled ashore. After the dinosaurs fell, small warm-blooded mammals took their first tentative steps into a quieter world. Each extinction cleared space, not just physically, but ecologically, for something unexpected to begin. We know about these events not because anyone was there to witness them, but because the Earth keeps a kind of diary. Every layer of sediment, every fossil fragment, every chemical signature is a whisper from a vanished era. Scientists read these clues like ancient scripts. They study changes in fossil diversity, spikes in elements like iridium, patterns in carbon isotopes, and the strange silences that appear in once busy geological records. These silences, the sudden absence of coral reefs, or the abrupt disappearance of ammonites, are just as loud in their own way as the presence of fossils. The 5 great mass extinctions we'll explore tonight happened across nearly 500 million years. Each had its own cause, its own mood, and its own strange survivors. They are the Ordovician-Silurian extinction, the late Devonian extinction, the Permian-Triassic extinction, the Triassic-Jurassic extinction, and the Cretaceous-Paleogene extinction, the one that famously ended the age of dinosaurs. But our goal tonight isn't to memorize names or dates, it's to feel what it might have been like to live in those times, to imagine the world not as we know it now, but as a layered, ever-changing planet, sometimes frozen, sometimes burning, sometimes gasping for air, and always, always recovering. Slowly, patiently, beautifully. Because that's the real wonder, not that life ended, but that it always began again. So take a breath, let your shoulders drop, and imagine yourself standing on the edge of the Ordovician Sea. The air is thick with nothing. No bird song, no buzzing flies, no trees rustling in the breeze, just wind over shallow water and the distant clicking of trilobite shells. It's a different world, but one that feels, strangely, like a memory. And this is just the beginning. Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us somewhere ancient, deeper than history, older than bones. We're going to drift through the 5 great mass extinctions of Earth, those moments when life itself teetered on the edge of nothing, and yet, somehow, returned. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the history of extinction. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. The idea of extinction is, in some ways, the ultimate bedtime story. It's both an ending and a beginning. A reminder that even the mightiest forms of life, the toothy, the towering, the radiant, can vanish without ceremony, leaving behind only a fossil or a void. And yet life has never stayed gone for long. It withdraws, regroups, changes shape, and reappears in forms both familiar and strange. To understand extinction, then, is to understand something deeper about time, about adaptation, and about the fragile yet astonishing resilience of life. Let's begin by asking, what is a mass extinction? You might imagine extinction as a slow fading, like a candle sputtering out, and that's true for most species. The vast majority of extinctions happen quietly, gradually, almost politely. Scientists call this background extinction, the natural rate at which species disappear due to changing environments, competition, or bad evolutionary luck. It's the soft tide of loss that hums beneath the ongoing symphony of life. But a mass extinction is not a tide. It is a wave, sudden, massive, and global. In these moments, Earth loses at least 3/4 of its species in what is, geologically speaking, the blink of an eye. And it doesn't just lose individuals, it loses entire lineages. Whole ecosystems unravel, niches collapse. The ancient sea that once shimmered with trilobites might suddenly go still. The forest that buzzed with dragonflies might fall silent, and the sky that once darkened with reptilian wings might hang empty for a long time. There have been 5 of these great events. Each one changed the direction of life on Earth, and in between there were long periods of stability, times when life diversified, sprawled, grew extravagant, times when ecosystems became intricate tapestries, with every thread carefully woven by evolution. But then, With a shift in climate or a burst of volcanic fury or a rock from space, everything would come undone. It's tempting to think of mass extinctions as stories of destruction. But they are also stories of reinvention. The end of one world has always made way for the birth of another. After the trilobites vanished, new kinds of fish began to dominate. After the great forest collapsed, tiny tetrapods crawled ashore. After the dinosaurs fell, small, warm-blooded mammals took their first tentative steps into a quieter, world-each extinction cleared space, not just physically but ecologically, for something unexpected to begin. We know about these events not because anyone was there to witness them, but because the Earth keeps a kind of diary. Every layer of sediment, every fossil fragment, every chemical signature is a whisper from a vanished era. Scientists read these clues like ancient scripts. They study changes in fossil diversity, spikes in elements like iridium, patterns in carbon isotopes, and the strange silences that appear in a once busy geological records. These silences, the sudden absence of coral reefs, or the abrupt disappearance of ammonites, are just as loud, in their own way, as the presence of fossils. The 5 great mass extinctions we'll explore tonight happened across nearly 500 million years. Each had its own cause, its own mood, and its own strange survivors. They are the Ordovician-Silurian extinction, the late Devonian extinction, the Permian-Triassic extinction, the Triassic-Jurassic extinction, and the Cretaceous-Paleogene extinction, the one that famously ended the age of dinosaurs. But our goal tonight isn't to memorize names or dates. It's to feel what it might have been like to live in those times, to imagine the world not as we know it now, but as a layered, ever-changing planet, sometimes frozen, sometimes burning, sometimes gasping for air, and always, always recovering, slowly, patiently, beautifully. Because that's the real wonder, not that life ended, but that it always began again. So take a breath, let your shoulders drop, and imagine yourself standing on the edge of the Ordovician Sea. The air is thick with nothing. No bird song, no buzzing flies, no trees rustling in the breeze, just wind over shallow water and the distant clicking of trilobite shells. It's a different world, but one that feels strangely like a memory. And this is just the beginning. If the Earth could speak, its voice would be stone. It wouldn't shout or sing or whisper in the way we do, but it would hum gently through the layered silence of time. Each layer of rock, each ripple of sediment, holds a sentence in a language we've slowly learned to read. And that's how we know. Not through tales passed down or photographs taken, but through the slow choreography of geology and the quiet testimony of fossils. Let's begin with a thought. Imagine baking a lasagna. Yes, really. Each layer you place, sauce, pasta, cheese, is a moment in time. Once it's cooked and cooled, if someone were to slice it open, they'd see the past arranged in perfect sequence. Now imagine Earth doing this not over an hour in an oven, but over millions of years. Layers of dust, ash, mud and minerals settle across ocean floors, deserts, swamps. Compressed by time, lifted by tectonics, exposed by erosion. These layers become pages in Earth's long stony diary. Scientists call this stratigraphy, the study of layered rocks. And like a gentle archaeologist of worlds long gone, a paleontologist can walk into a canyon or a quarry and, by reading the rocks, glimpse not just what lived there, but when, and how, and sometimes even why it vanished. Embedded in these layers are fossils, the mineralized remains of ancient creatures. Some are as familiar as a curled ammonite, others as strange as a fern frozen in stone. But what's most revealing isn't always what's there. Sometimes it's what suddenly isn't. When an entire group of fossils disappears from the rock record, from coral reefs to trilobites to towering tree-like lycopods, it suggests something profound. A global change, rapid and unforgiving. These abrupt disappearances are the first fingerprints of mass extinction. Now and then, these shifts leave more than just silence behind. They leave signals, traces of catastrophe that stretch across continents. One of the most famous is a thin, dark line found in rocks all around the world. It's rich in iridium, a rare element on Earth's crust but common in asteroids. This line marks the end of the Cretaceous period, when the dinosaurs fell, and it's the quiet residue of a rock from space. But even without asteroids, Earth marks its grief in other ways. Ash layers from ancient volcanic eruptions, telltale changes in the ratio of carbon isotopes, subtle shifts in sediment grain. All of them are threads in a tapestry we've learned to follow. Each shift, each tilt, each pattern hints at something larger. Rising oceans, falling temperatures, acidifying seas. Let's gently pause here and consider just how extraordinary this is. We're tiny, fleeting creatures, and yet we've learned to read the deep history of a world that existed before there were eyes to see it. We've found ways to trace extinction, not by looking forward, but by looking down, into the layers, into the memory of stone. There's a beautiful humility in this, because the fossils we find aren't evenly distributed. Some layers are rich with shells and bones, while others are barren, like a skipped page. Not every creature fossilized. Most never did. The conditions had to be just right. Rapid burial, low oxygen, mineral-rich waters. And so, what we find is always partial, like fragments of a lullaby lost to time. We're piecing together a song with only a handful of notes, and yet, somehow it's enough. Enough to know that there was once a time when dragonflies the size of dinner plates filled the skies, and when oceans held forests of glassy sponges. Enough to know that 5 times the world convulsed and life almost vanished. Enough to know that after each collapse something new began, slowly but always surely. There's also something comforting in the idea that the earth remembers even when we do not. That beneath our feet lies not just rock, but memory. Not just minerals, but echoes. So next time you hold a stone in your hand, or walk along a cliff face, or see a fossil resting quietly behind glass, you'll know. This isn't just a curiosity, it's evidence, a message, a bookmark from a chapter that ended long before you began. And perhaps, like all stories, it still echoes in the world we know now. In our next part of the journey, we'll leave behind the method and dive into the first extinction itself. We'll descend into the Ordovician Sea, a world without trees or insect or birdsong, but rich with life all the same. And there, in a moment of cooling, of silence, of stillness, we'll see how quickly everything can change. But for now, just breathe. Let the thoughts settle like dust on the floor of an ancient ocean, because every extinction begins not with a bang, but with a shift, a drift, a slow turning of the page. Close your eyes for a moment and try to imagine Earth as it was nearly 500 million years ago, around 445 million years in the past. There are no trees, no birds, no land animals, no flowers or grass beneath your feet. In fact, there's barely any life on land at all. The world is quiet above the waves, almost untouched. But beneath the surface of the sea, in shallow continental shelves and sunlit lagoons, life flourishes. This was the Ordovician period, a time when Earth was a water world. The continents were scattered and smaller than today, most of them clustered in the southern hemisphere, slowly drifting as if in a dream. One supercontinent, Gondwana, was beginning to drift closer to the South Pole, and that slow movement, that gentle slide of land over time, would set the stage for the first great act of extinction in our planet's memory. But before we get to endings, let's sit with what was. Let's explore the life that filled the Ordovician seas, drifting and crawling and anchoring itself in a world more alien than familiar, and yet somehow still deeply connected to us. The oceans at this time teemed with creatures unlike anything you'd find today. Trilobites, those armoured, many-eyed arthropods scuttled across the sea floor like careful janitors of the mud. Some were small enough to rest on the tip of your finger. Others could grow as large as a dinner plate. They had existed since the Cambrian explosion and were among the first to wear skeletons on the outside like nature's earliest knights. Above them floated graptolites, tiny colonial animals that resembled wisps of ink frozen in shale. Though simple, they were widespread and diverse, drifting through the water column in droves, feeding on microscopic particles and leaving behind beautiful fractal-like fossils in stone. Further down the food chain lived a host of filter feeders, brachiopods that clung to rocks like ancient clams, their shells opening and closing in rhythmic stillness, and crinoids, sometimes called sea lilies, waving gently with the current on long stalks. Coral reefs were just beginning to form, made not by the hard corals of today, but by early versions, simple, primitive, but still home to a bustling web of marine life. Then there were the nautiloids, predators of the open water, jet-propelled and elegant, some of them stretching several metres long. These ancient relatives of squid and octopuses drifted with intent through the ocean, their tentacles probing, their hard shells gleaming like underwater lanterns. They were among the apex predators of their time, ruling a world without jaws but full of innovation. What makes this world so fascinating is its silence. Not literal silence, of course. There were currents and storms and the soundless pulse of marine life, but a kind of ecological silence. No buzzing flies, no bird song, no mammalian cries, no leaves rustling. Land was barren, home only to rocks and wind, and perhaps a few mossy intruders testing the edge of the sea. And yet, in that quiet, marine life was experimenting, evolving, diversifying in ways it never had before. This period saw one of the greatest biodiversification events in Earth's history, known to scientists as the Great Ordovician Biodiversification Event. Over millions of years, new species exploded into being. Ecosystems grew more complex. The seafloor became a living canvas of movement and form. This slow blooming of diversity wasn't driven by any single dramatic shift. Instead, it was likely the result of many small nudges, the rise of plankton that fed entire chains of life, the growing availability of ecological niches, the stabilization of climate and sea level. It was a time of relative peace, at least geologically speaking, and life took full advantage. But even in the most tranquil garden, change is always near. While marine life danced in the warm shallows, the earth itself was changing course. Gondwana, as it continued its slow southern drift, began to move into colder latitudes. As it approached the South Pole, it triggered the growth of vast ice sheets, locking up water in frozen silence. This shift didn't happen in a day. It took thousands of years. But in the long view of deep time, it was fast. Sea levels began to fall as more and more water became ice. Shorelines retreated. Shallow seas vanished. Habitats that had taken millions of years to flourish were lost in a geological blink. The creatures of the Ordovician, so well adapted to their precise environments, had little time to adjust. The trilobites that had scuttled so confidently, the graptolites that had drifted so freely, the coral reefs, delicate and intricate, all began to suffer. The ocean grew colder, its chemistry shifted, ecosystems began to unravel. And so, as we end this session, you might imagine yourself standing on the shore of one of those disappearing seas. The wind colder now, the tide lower than yesterday, the sky wide and empty above you. In the water, fewer trilobites scurry, fewer shells gleam. The silence feels heavier, as if the world is holding its breath. What comes next will be even quieter. The first of Earth's 5 great mass extinctions is about to begin. But even here, at the edge of the fall, the memory of the sea remains, and soon we'll drift into the moment when that memory nearly disappears. The story of the first mass extinction doesn't open with a crash or a fire. It begins with a soft chill, a long, creeping silence that settled over the planet. It began when the landmass of Gondwana drifted ever southward, inch by inch, until it reached the polar regions of the globe. There, blanketed by a weaker sun and aided by falling carbon dioxide levels, it gave rise to something Earth had not seen before: a great glacial stillness. What followed was one of the coldest chapters in Earth's history up to that point. Glaciers spread across the southern hemisphere, growing taller, wider, hungrier. As they expanded, they drew in vast amounts of seawater, locking it away as ice. Global sea levels dropped. Shallow coastal habitats, where much of the Ordovician biodiversity had blossomed, vanished almost overnight. The warm lagoons where trilobites had fed and graptolites had drifted turned to barren mudflats. Coral reefs, fragile and fixed in place, were left stranded above the waterline or buried under sediment as the oceans pulled back. It was a sudden, silent suffocation. For life forms that depended on precise conditions, specific temperatures, salinities and depths, this shift was more than inconvenient. It was fatal. And unlike modern animals which can sometimes migrate or adapt quickly, Ordovician species were far less mobile and much more specialised. Many were filter feeders, anchored to the seafloor or drifting in the upper ocean, unable to escape the changing tides. This was the first pulse of the Ordovician Silurian extinction, a planetary shiver that swept across shallow seas and left behind fossils frozen in time. Whole reef systems vanished. Over 85% of marine species were lost. Not in a single day, but across tens of thousands of years, a long sigh of loss in geological time. But the extinction was not finished. As the glaciers reached their peak, they began, inevitably, to melt. The Earth warmed again. Sea levels rose, pouring back into the basins they had abandoned. You might expect this to be a moment of relief for marine life, returning waters, returning habitats, but the oceans were no longer the same. The melting ice sheets flushed fresh water and nutrients into the seas, disrupting currents and layering the water in ways that prevented oxygen from reaching deeper levels. The bottom of the ocean, once home to benthic creatures and coral forests, became a dark, breathless place. In this deoxygenated world, microbial life flourished. Bacteria that thrived in low oxygen environments began to bloom, releasing hydrogen sulfide and further poisoning the water. This was the second pulse, not one of ice, but of rot. It's a haunting image, not fire or flood, but a kind of global drowning in silence. Creatures that survived the cold were undone by the return of warmth. The ocean, which had once given life, became a place of stillness and death. The graptolites, so numerous and varied, dwindled. The trilobites, though survivors of previous changes, could not adapt fast enough. Brachiopods, corals, nautiloids, all suffered heavy losses, and yet even here, in the aftermath of absence, the Earth stirred with new beginnings. What survived the Ordovician extinction? Mostly the small, the simple, the unassuming. Organisms that could tolerate wide ranges of oxygen levels or live in deeper, more stable environments. Tiny plankton, early vertebrates, and the ancestors of future reef builders slowly repopulated the oceans. The biodiversity was diminished, yes, but the stage was reset. New players, new ecosystems, new evolutionary experiments would follow. The fossil record shows that after this extinction, marine ecosystems looked very different. Coral reefs rebuilt themselves, this time with new architects. The food web rearranged. Predators and prey adapted to new dynamics. Some species that had been rare became dominant. Others vanished forever, remembered only in stone. Scientists believe that this event, the sudden freeze followed by the suffocating thaw, may have been one of the earliest times Earth's climate swung so dramatically and with such devastating ecological consequences. But perhaps what's most remarkable isn't how many species were lost, but that life recovered at all. Because from our modern perspective, looking back across 500 million years, it seems almost impossible that such devastation could be reversed. And yet, slowly, quietly, life returned. It always does. There is something deeply humbling in this. Earth has not always been kind. Its climate has lurched between extremes. Its surface has been struck, drowned, burned, frozen. And yet through it all life persists. Not always the same life, not always in the same form, but life nonetheless. It adapts, it endures, it evolves. And even after the silence of extinction it sings again. As we leave the Ordovician behind, we carry with us a memory of that ancient sea. A time when the world was still new, when life clung to the margins, and when the first great loss made room for the next great beginning. In our next chapter, we'll surface into the Devonian period, a world of armoured fish, towering plants, and quiet collapses that unfolded not with a bang, but like a breath held too long. A different kind of extinction. Slower, stranger, but no less profound. For now, though, rest. Let the image fade. Ancient ice, vanishing tides, and the ocean sighing softly as it learns once again how to breathe. If the Ordovician extinction had been sudden, cold, and brutal, a sharp fracture in the fabric of life, then the Devonian extinction would unfold like a slow unravelling. The planet itself was not in crisis at first glance. There were no asteroid strikes, no massive, volcanic plains bubbling with fury, at least not yet. Instead, it began with growth, with success, with the quiet triumph of plants. Let's step gently into the Devonian period, a span of time stretching from about 419 to 359 million years ago. It's often called the Age of Fishes, and with good reason. The seas were alive with movement, more intricate, more dynamic, more dramatic than ever before. Placoderms, jawed armoured fish, glided through coastal waters like tanks with fins, their bony plates shining dully in the dim light. Some were small, others grew to terrifying lengths, their jaws capable of crushing whatever crossed their path. They ruled these waters as apex predators long before sharks took the crown. Elsewhere, shoals of ray-finned fish wove through kelp-like seaweed, while lobe-finned fish, those strange muscled swimmers with bones in their fins, hugged the murky bottoms of estuaries and tidal pools. They were not yet walkers, not yet breathers of air, but the potential was there, quietly biding its time. Above the waves, something even more profound was taking root, literally. For the first time in the Earth's history, landscapes were beginning to change in colour, not just with the scattered greenish films of algae or the occasional moss-like pioneer, but with true vascular plants. These were no longer just small green smudges hugging rocks. They were becoming forests. Early land plants had developed something new. Roots. Simple at first, then deeper, stronger. Roots broke down rock, creating new soil. Leaves spread into the air, capturing sunlight more efficiently. With these advances came a profound change in how Earth breathed. As roots dug into the crust, they accelerated chemical weathering, a slow process by which rock is broken down into minerals and soil. But this weathering also removed carbon dioxide from the atmosphere, locking it away in sediments and shells. The result? The Earth's climate cooled, gradually but steadily, and so, paradoxically, while life was thriving, it was also sowing the seeds of its own undoing. These vast new plant networks, beautiful and sprawling, caused rivers to meander and flood in new ways. They trapped sediment, redirected erosion, and created the first true landscapes: valleys, floodplains, soil-rich basins. But they also unleashed nutrients into waterways, especially phosphorus, a fertilizer for algae. And algae, when fed too much, bloom out of control. As these blooms spread through lakes, estuaries, and even shallow seas, they consume the oxygen in the water. The process is known as eutrophication, and it creates anoxic conditions, waters without oxygen. Nothing large can survive long in such places. Fish suffocate, invertebrates vanish, coral reefs collapse, life retreats slowly from the shallows it had once dominated. But again, it was not just one event. The Devonian extinction was not a single disaster, but a slow and staggered series of ecological collapses. Scientists describe 5 major pulses of extinction spread across 20 million years. That's longer than humans have existed, longer than the age of dinosaurs, long enough for life to begin recovering only to stumble again. Each pulse brought new challenges, sometimes a climatic shift, sometimes changes in ocean chemistry, sometimes prolonged anoxia. Coral reefs, which had once reached a dazzling peak in diversity and complexity, would not fully recover until tens of millions of years later. For a long time, the ocean floor felt eerily quiet, and yet it was not a total erasure. Life continued, not untouched but not destroyed either. What's so quietly astonishing about the Devonian is that much of the change came not from cataclysm, but from biology itself. It was life, plants, roots, the spread of forests that altered the planet's systems. The Earth was not struck by something foreign. It was changed by its own children. And this makes the Devonian extinction feel somehow closer, more intimate. It is a story of cascading effects, of unexpected consequences, of ecosystems growing more complex, more interwoven, and therefore more fragile. It is, in a way, a mirror. A very distant one. But when you consider that today's environmental shifts are also driven by biological activity, our own, you can begin to sense how the Devonian slow-motion unravelling might still echo in the present. As we drift out of this session, picture a Devonian coast. There's greenery now, strange and sparse, but rising. The forests are shallow and primitive, but they cast shadows. The rivers run muddy. The sea has grown murkier. The coral reef you saw as a child would now be gone, replaced by algae mats and silence. And somewhere beneath the muck, the ancestors of amphibians are learning to wait out the collapse. The world is changing, not all at once, but inch by inch, leaf by leaf, root by root. If you could float gently above a Devonian coastline, what you'd see below might at first glance resemble a moment of triumph. Verdant riverbanks traced with fern-like plants, hills smudged green with the earliest forests, shoals of fish threading the water, their scales catching the sunlight like ripples of silver. It looks peaceful, stable even. But beneath that surface, something quiet and lethal was building. The Devonian extinction wasn't loud. It didn't happen in a single day or year. Instead, it unfolded like a page curling slowly in the sun. In the beginning, most organisms likely didn't notice anything was wrong. There were no immediate signs of collapse, no sky-darkening impact, no volcanic thunder, just small changes, tiny shifts, and then more of them. Forests by this time had spread further inland. Their roots had grown deeper, their leaves broader, and with their expansion came a cascade of consequences. The newly vegetated landscapes were transforming erosion patterns, guiding rivers along new paths, and delivering ever larger amounts of nutrient-rich sediments into nearby waterways. These nutrients, especially phosphorus, acted like an uninvited feast for algae. And algae, when well fed, do not grow politely. They bloom. The phenomenon is not unfamiliar to us today. You may have heard of modern algal blooms choking lakes or forming massive slicks in coastal waters, robbing the environment of oxygen as they die and decay. The Devonian version was much the same, but on a global scale. Entire marine basins began to experience episodes of ocean anoxia, where oxygen levels fell so low that only microbial life could survive. And this lack of oxygen wasn't merely unpleasant, it was terminal. Fish suffocate just as surely as mammals do. Coral and sponge reefs, already weakened by previous stresses, found themselves unable to recover. Crinoids, brachiopods, trilobites all began to decline. The process wasn't constant. It came in waves, 5 major extinction pulses that rippled over a span of roughly 20 million years. Some pulses were more intense than others. Some wiped out entire families of species. Others disrupted ecological balances just enough to trigger a chain reaction of collapses. In between, there were pauses, moments when life began to recover, only to be set back again. The Devonian extinction is unusual for this on-again, off-again rhythm. It was not a single cataclysm, but an era of prolonged instability. And that instability, in its own strange way, became the defining trauma of the period. Geologists studying the rock record have found black shale deposits from this time, evidence of stagnant, oxygen-starved seas that stretched across vast areas of the ocean floor. These layers are dark not only in appearance, but in implication. They speak of a world where decay outpaced growth, where the breath of the ocean had gone shallow. In these toxic waters, microbial communities thrived, while complex marine ecosystems withered. The great coral reef systems of the Devonian, among the most extensive Earth has ever known, disappeared and would not return in full form for another 100 million years. What makes this extinction feel so peculiar is that, unlike later events, there was no single villain. The asteroid of the Cretaceous, the volcanism of the Permian. In the Devonian, it was the plants. It was, to put it softly, a side effect of success. The forests didn't know they were sowing the seeds of collapse. They were simply doing what evolution taught them to do, growing, spreading, reaching. But their triumph reshaped the planet's chemistry. The Earth cooled as CO2 was pulled from the sky. The rivers thickened with silt. The oceans grew still, then breathless. And yet, even within this long twilight, life endured. In deep waters, in isolated pockets, in muddy shallows too chaotic for algae to overwhelm, species clung on. Small, adaptable creatures, generalists, rather than specialists. A trend we'll see again and again. Among these survivors were lobe-finned fish, already developing the sturdy jointed fins that would one day become limbs. Tiktaalik, the famous transitional fossil, comes from this era. A flat-headed fish with the beginnings of a neck, perhaps even the suggestion of a wrist. It's unclear how directly these creatures were impacted by the extinction events, but one thing is certain. In the shadows of collapse, evolution was laying foundations. The Devonian world was still rich with promise, even as it emptied itself out. As we drift toward the next session, imagine a reef, once bursting with colour and motion, now silent and skeletal. The water is darker, the algae cling in patches, the current is sluggish, and somewhere, under a rotting log in a muddy stream, a small creature peers upward toward the dim surface, lungs and gills both working, unsure which it might need next. The sea is sick, but the story isn't over. Mass extinction is not a clean slate. It does not erase everything. It reshuffles, it narrows, it reconfigures the rules. In the aftermath of the Devonian's long unravelling, what remained was a quieter ocean, a simpler reef, and a world that had lost much, but not all. And in that silence, a few persistent forms began to shift, to explore, and to venture into the unknown. By the time the Devonian period drew to a close, the once glorious placoderms, those jawed, armoured fish that had once ruled the seas, were gone. Their heavy bony plates, once a sign of dominance, had become burdens in a changing environment. They couldn't adapt quickly enough to low oxygen, to shifting food webs, to the new rhythm of a planet in flux. They vanished, leaving behind only impressions in stone and the soft echo of power lost. But not all fish shared their fate. Two lineages in particular, both seemingly modest at the time, endured: the ray-finned fish and the lobe-finned fish. The ray-finned fish, with their delicate fan-like appendages, would go on to become the most diverse group of vertebrates on Earth. They fill today's rivers, lakes, and oceans. But during the late Devonian, they were not yet dominant, just survivors, keeping close to niches where the water still flowed and the oxygen still lingered. The lobe-finned fish, however, took a different path. Their fins were thicker, fleshier, supported by a sturdy internal skeleton. They could prop themselves up, perhaps awkwardly at first, in shallow pools. Some had developed primitive lungs in addition to gills, allowing them to gulp air in stagnant waters where others suffocated. These adaptations weren't planned. Evolution never plans. But they proved useful in a world of dying seas and vanishing coastlines. One of the most famous examples of this lineage is Tiktaalik, whose fossil was discovered in the Canadian Arctic. It's often described as a fishapod, something halfway between a fish and a tetrapod. It had a neck, ribs, and a flat skull. It could push itself up on its fins, raise its head above water, perhaps even drag itself between pools. It was not yet walking, not truly, but the potential was there, resting in cartilage and bone. What's remarkable is that this transition from water to land was not a dramatic leap. It was not a moment of conquest. It was a slow and uncertain shuffle. These creatures likely lived in swampy environments where tides and floods carved shifting boundaries between land and sea. And as extinction swept away the dominant forms, these adaptable pioneers found room to experiment. Beyond the fish, other survivors also stepped forward. Early amphibians, primitive insects, and arthropods that had tiptoed onto land before the worst of the extinction found new opportunities in a landscape that was, for the first time, rich with plants, but light on predators. It's worth pausing here to consider that before this, there had never been forests, never been shaded ground or leaf litter or roots to tangle through. Now there were, and that changed everything. The soil itself became something new. No longer just loose rock and sand, it was alive, interlaced with fungi, microbes, decaying leaves. It held moisture, it supported ecosystems, and it became a home not just for plants but for the animals that followed them. The Devonian extinction then created not just vacancies in the ocean, but real estate on land. In the oceans, recovery would take time. Coral reefs remained sparse, filter feeders returned slowly. But in freshwater systems, rivers, lakes, deltas, evolution picked up speed. These were the crucibles of experimentation, and from them, the future vertebrates of land would eventually crawl, blink, breathe, and begin to walk. The story here is not one of triumph. Not yet. It is one of quiet endurance, of bodies reshaped by hardship, of gills turning slowly into lungs, of fins turning gradually into fingers. These were not the loud winners of evolution. They were the patient ones, the flexible ones, the ones who could hold on just long enough for the world to change again. And it would. It always does. As we leave the Devonian behind, we step into a different kind of world, one where vertebrates are learning to rise onto four legs, where forests are deepening, darkening, where insects begin to take flight. The seas remain unstable, but the land is coming alive. It's a bittersweet image. The reefs lie broken. The oceans have lost their colour. But on a distant riverbank under the shade of a spindly tree, a small creature crawls forward, blinking at the light. And in that soft movement, the story of life on land begins to unfold. Before the world burned, it was full, strange, bustling, complex. The late Permian period, just before the greatest extinction Earth has ever endured, was not a bleak time. It was a crescendo, a flourish, a vast and humming harmony of land and sea, life sprawling across every available surface, as if, trying to fill the planet with every possible shape it could imagine. On land, the continents had finally drawn together. What had once been scattered islands and isolated masses had coalesced into a single, immense supercontinent known as Pangaea. This was a land of extremes, harsh deserts in the interior, lush forests nearer to the coasts, and towering mountains that cast long shadows over primeval valleys. Pangaea was so vast that its interior was likely arid and hostile, far from the moderating effects of the ocean. Weather patterns were unfamiliar, seasons were more intense, and yet life found a way to adapt. The terrestrial ecosystems of this time were teeming with creatures both familiar and alien. Synapsids, the ancestors of mammals, were particularly dominant. Some looked like scaled reptiles, others resembled something halfway between a lizard and a saber-toothed cat. There were sprawling herbivores with barrel-shaped bodies and thick, stumpy legs, creatures like Scutosaurus plodding through fern-covered plains, and predators like Gorgonops, with long teeth and forward-facing eyes, patrolled the underbrush in search of prey. Amphibians still lingered in many wet environments, larger than their modern counterparts, and more varied. There were broad-headed species that lurked at the bottom of swamps, waiting in stillness. And in more open spaces, small reptiles scurried under cycads and early conifers, darting from shade to shade. In the seas, life had reached new levels of diversity. Sponge reefs, made not of coral, but of delicate sponges and microbes, stretched across warm, shallow waters. Brachiopods, with their symmetrical shells, dotted the seafloor in immense numbers. Ammonoids, relatives of modern squids and octopuses, spiraled through the water in elegant coils. There were crinoids, waving like underwater ferns, fusulinids, rice-sized foraminifera that blanketed the sediment in dense communities, and trilobites, though in decline, still clinging to their lineage in the quieter corners of the deep. It was a world in full bloom, yet it was also fragile. The interconnectedness of these ecosystems, what made them so vibrant, also made them vulnerable. A change in temperature, a disruption in chemistry, a shift in ocean current, any of these, if large enough, could set off a cascade. And the Earth was already restless. The end of the Permian was approaching, though no creature living at the time could have known. There were no alarms, no omens that would be clear in retrospect. But beneath the surface the planet was shifting. Tectonic forces, always slow, always steady, had been building pressure under what is now Siberia. Magma began to gather, gases stirred, and then, over a span of hundreds of thousands of years, fast by geological standards, the Earth would erupt with such violence, such persistence, that the very balance of the biosphere would collapse. But not yet. For now, imagine walking across a Permian's landscape. The air is warm, perhaps dry. The plants around you are tall, spindly, with waxy leaves to conserve moisture. The ground is red with iron-rich soil. Somewhere nearby, a synapsid trundles through a grove of tree ferns, flicking its head to scatter biting insects. Overhead the sky holds no birds, none have yet evolved, but it is not empty. Winged insects, some as large as your outstretched hand, trace lazy arcs in the sun. Everything seems steady, balanced, as though Earth, after billions of years of experiment, has finally found a rhythm. But deep within the planet, pressure is rising. The floor beneath your feet is preparing to crack open, and when it does, everything will change. This is the tragedy of the Permian. Not that it ended something broken, but that it ended something thriving. And yet, perhaps that's what makes it such an important chapter in Earth's story. A reminder that no matter how lush the forest, no matter how crowded the reef, the rules of life are always temporary. And in the long arc of deep time, even the most vibrant symphony can fall suddenly, jarringly silent. In the next session, will open the door to that silence. The volcanoes will begin to rise, the oceans will forget how to breathe, and the great dying will begin. When we think of the end of the world, we often imagine it happening all at once. A sudden fireball, a falling sky, a thunderclap of extinction that silences everything in a moment. But the greatest extinction in Earth's history did not arrive with a bang. It rose slowly, inexorably, from deep within the Earth. It hissed. It boiled. It choked the sky with ash and the seas with silence. Around 252 million years ago, in what is now northern Siberia, the ground opened. For hundreds of thousands of years, wave after wave of volcanic eruptions poured molten basalt over the land, covering millions of square kilometres. This geological event, known as the formation of the Siberian Traps, was not just a lava flow. It was a planetary transformation. With each pulse of magma, enormous amounts of carbon dioxide were released into the atmosphere, and not just CO2. The burning of underground coal beds released methane, a greenhouse gas even more potent. Sulfur dioxide billowed into the skies, creating acid rain that fell like vinegar on forests and reefs. The air grew heavy with toxins. The climate, once stable, began to spiral. Global temperatures rose, by some estimates, as much as 8 to 10 degrees Celsius in a relatively short geological window. The oceans, which absorb much of the planet's excess heat and CO2, became hot and acidic. Coral reefs dissolved. Shells thinned and vanished. And worst of all, oxygen, the invisible thread that ties marine life together, began to disappear. The ocean, in many places, simply forgot how to breathe. As warm water holds less oxygen than cool, and as circulation patterns were disrupted by the warming climate, vast regions of the sea became anoxic. In these suffocating zones, dead organic matter collected and rotted, feeding microbial blooms that in turn released hydrogen sulfide, a toxic gas deadly to most complex life. There is evidence that this gas, once concentrated enough, may have even seeped into the atmosphere, poisoning coastal ecosystems and damaging the ozone layer. If that happened, ultraviolet radiation would have scorched the land, compounding the disaster. This was not a short-lived crisis. The Permian Triassic extinction event, sometimes simply called the Great Dying, unfolded over tens of thousands of years, long enough for some species to begin adapting, only to be struck down again by the next wave of climate upheaval or oceanic stagnation. The biosphere didn't collapse all at once. It was peeled back layer by layer until only the barest skeleton of life remained. In the oceans, the devastation was almost total. Roughly 96% of marine species vanished. Trilobites, which had survived every extinction until now, were gone. Tabulate and rugose corals, once the architects of reefs, disappeared entirely. Brachiopods, crinoids, ammonoids, whole lineages decimated. The sponge reefs that had adorned the Permian seafloor collapsed into lifeless rubble. On land, the losses were equally grim. 70% of terrestrial vertebrate species perished. Entire ecosystems of synapsids, amphibians, and large herbivores were wiped out. Forests withered and retreated. In many places, soils eroded down to bedrock. Insects, normally resilient, suffered their only known mass extinction. It is difficult to comprehend the scale. Earth was not merely changed, it was emptied. The fossil record from this time often shows what geologists call a survival fauna, a simplified, stripped-down community dominated by a few hardy generalists. In place of the rich diversity once found in reef systems or river deltas, we see monotony. Few species, fewer interactions, a biosphere reduced to whispers. And yet, even in this bleakness, something persisted. A small handful of species endured. Some scientists speculate that organisms capable of tolerating wide environmental extremes, heat, acidity, low oxygen, had the best chances. Others point to geographic luck, with isolated pockets of habitable zones where conditions remain just bearable. Whatever the reason, life did not vanish completely. And that small flame of survival made all the difference. Why did this happen? Why did volcanic activity cause such widespread destruction this time, when Earth had experienced eruptions before? Part of the answer lies in the scale. The Siberian traps were among the largest volcanic events in Earth's history, but also in the timing and the feedback loops. Once global temperatures began to rise, the planet's own systems responded in ways that amplified the crisis. Melting permafrost released more methane. Dying plants no longer absorbed CO2. The collapse fed itself. It was a tipping point. And once, past, Earth needed time, millions of years to rebalance. As we drift to the next session, picture the landscape. Barren, scorched, quiet. Rivers run sluggishly through grey plains. The sea is opaque with decay. The air tastes faintly of ash. There is no bird song, birds do not yet exist, and no buzz of insects. Just stillness, just absence. But also a beginning. From this great dying, something new will rise. In the long, hollow quiet after the Permian extinction, a different kind of life emerged to fill the emptiness. Not with bright colours or movement, not with the flicker of fins or the shuffle of limbs, but with something simpler, slower, more patient, fungi. For a time, after the fire and flood, it was the decomposers who reigned. In the fossil record, this strange dominion is captured not through bones or shells, but through spores, tiny, resilient traces left behind in layers of sediment. Across multiple sites on multiple continents, researchers have found thick deposits rich with fungal spores, especially just above the boundary that marks the end of the Permian period. These aren't the kinds of fungi we recognise from our dinner plates or damp basements. They were simpler forms, likely moulds and other microbial decomposers, yet they thrived in the world left behind. A world stripped of forests. A world covered in the carcasses of fallen creatures. A world where photosynthesis faltered and detritus was everywhere. It's a haunting image. Earth, quiet and grey, blanketed not with green but with rot. The air would have been acrid. The soil loose and depleted. Rivers sluggish with the remnants of forests washed away. With so few living animals to scatter seeds or pollinate, plant life would have struggled to re-establish itself. Grass had not yet evolved. Flowers were still millions of years away. And trees, those titanic engines of carbon capture and shade, were now ghosts in the fossil record. And so the fungi came. Not in conquest, but in service. Their role was not to dominate, but to break down what remained. They digested the past, returning carbon to the atmosphere, cycling nutrients through a world desperately in need of repair. They covered logs and bones, filled the cracks between rocks, and spread in networks so fine they seemed invisible, yet so vast they could bind a landscape together. For a moment in Earth's history, decomposition was the planet's most vital function. Alongside the fungi, a few survivors crept into view. Chief among them was a squat, pig-sized creature with a barrel chest and a blunt snout, Lystrosaurus. This humble synapsid, sometimes likened to a reptilian bulldog, became one of the most successful animals in the early Triassic. Fossils of Lystrosaurus have been found across much of what was once Pangaea, from South Africa to Antarctica to Asia. Lystrosaurus was not flashy. It had no claws to speak of, no armour, no speed, but it could burrow, it could tolerate extreme environments. It may have had a high tolerance for CO2 or low oxygen conditions, and perhaps most importantly it could eat almost anything green, assuming green things ever returned. For a while, the fossil record becomes strangely monotonous. Instead of the rich diversity that marked the Permian, we find layer after layer filled with Lystrosaurus bones and very little else. It's as if, for a time, Earth narrowed itself to a single storyline: survival by simplicity. But this narrowing was also a clearing. The ecosystem was broken, but that very brokenness created space. With the dominant species gone and the old food web shattered, evolution could begin again. Not by rebuilding the same structures, but by experimenting with new ones. Amphibians, which had once been abundant, were reduced to scattered remnants, but reptiles began to diversify. A new lineage of small, agile creatures, archosaurs, started to appear. They would one day give rise to the dinosaurs and eventually to birds. But for now, they were quiet background players, living in the margins of a world still gasping for air. The skies remained empty. The forests had not yet returned. The reefs were gone. But in puddles and burrows and shallow lakes, small creatures waited. And in the soil, fungi worked tirelessly. There's something poetic about this phase of Earth's story. A time when life's greatest role was to clean up, to process loss, to digest history. It reminds us that even the smallest organisms, the unseen, the slow, the silent, can shape a planet. That healing doesn't always look like growth. Sometimes it looks like decay. And that's not failure. That's how the next chapter begins. So the Earth rested, if such a thing can be said. It decomposed. It rewrote its chemistry. It let go of what was. And it gave fungi their moment. Not as kings, perhaps, but as caretakers of a wounded world. In the next session, we'll begin to see the light return. Not quickly, not cleanly, but steadily. Coral reefs will creep back into the shallows. Forests will rise once more, and the age of dinosaurs will stir beneath the warming soil. For now, let the image settle. A world covered in spore, in shadow, in the quiet work of things that do not shine. Because even here, life does what it always does. It waits and it works. When a forest burns, when the last leaf curls into ash and the last bird has flown, the ground remains, charred, blackened, stripped of its stories, but it remains. And slowly something finds its way back. A spore, a seed, a creeping root. The same is true of Earth after the great dying. What was left was not lifeless, but broken. What came next was not a return to what was, but the invention of something new. The early Triassic period was a time of transition, geologically, biologically, atmospherically. The Earth was hot, not just warm, but deeply, unevenly hot. With the Siberian trap still releasing gases and the carbon cycle still wobbling, the climate remained unstable for hundreds of thousands of years. Forests were scarce. Deserts were common. The poles, once icy refuges, now sweltered under tropical conditions. And yet, amidst this heat and hush, ecosystems began to reassemble. The first signs of recovery were small. Scattered plant life, mostly hardy conifers and seed ferns, began to return in patches. Their roots helped stabilize soil. Their leaves reintroduced organic matter to the surface. These weren't lush rainforests. They were sparse, scrappy, and prone to failure. But they were enough. In the oceans, reef-building organisms began to test the waters once more. Not coral, at least not yet, but other reef-forming creatures. Sponges, cyanobacteria, microbial mats. They laid the groundwork for the eventual return of reef ecosystems. But for tens of millions of years, these structures remained subdued, as if the oceans too needed time to remember how to sing. The recovery of biodiversity after the Permian extinction was slow, far slower than after any other mass extinction. It may have taken 5 to 10 million years before diversity levels even began to climb meaningfully. And for many groups, it took over 20 million years to fully reclaim their former ecological roles. This wasn't just due to bad luck or slow mutation rates. The extinction had been so complete, so structurally devastating, that the evolutionary ladder had been broken, not just climbed down. Entire groups had vanished. Entire ecosystems had been erased. The pathways of life had to be rebuilt from the roots up. But evolution is nothing if not creative. From the scattered survivors, new lineages began to rise. Among the synapsids, a group of small, upright walking forms called cynodonts began to diversify. These were not quite mammals, but they were on the path. Some had whiskers, some had differentiated teeth. Some may have been warm-blooded. They filled new ecological niches as insectivores and scavengers, and eventually, millions of years later, their descendants would suckle their young and build burrows and fly planes. But that part was still far away. At the same time, archosaurs, a group that includes crocodiles, dinosaurs and eventually birds, were starting to diversify. In the early Triassic, they were small, quick and often overlooked. But in the absence of large competitors, they began to expand into new environments. Some grew longer legs and became runners. Some grew stronger jaws and became hunters. They were evolutionary experiments, and the planet newly cleared gave them room to try. One of the most remarkable stories of this era is that of ecosystem repatterning. When life returned, it didn't simply recreate what had been lost. It built something different. New food webs, new predator-prey relationships, new body plans. The biosphere was not a copy of the Permian. It was a remix. The plants that recolonized the land were not the same species. The animals that filled the rivers were not simply smaller versions of what had come before. It was a world reshaped, not just rebuilt. In the fossil record, we begin to see evidence of renewed complexity. Predator tooth marks on prey bones, burrows in lake sediments, fossilized coprolites, fossil poop, hinting at digestive systems adapted to new diets. These traces are small, often overlooked, but they are signs that ecosystems were once again becoming interconnected. Life was weaving its web again. By the mid-Triassic, true dinosaurs began to appear. Not yet the titanic giants of the Jurassic, but small bipedal forms darting through ferny undergrowth, hunting insects and small prey. They would go on to dominate the Mesozoic era, but at this point they were still humble, still recent, still finding their place in a world that was only just beginning to allow ambition again. And slowly, reefs returned. Shallow seas became nurseries for fish. Forests thickened. Rainfall patterns stabilized. Oxygen levels rose. Species interactions grew more intricate. The great silence gave way to a quiet murmur, then a hum, then, eventually, a chorus. But it was not fast, and it was not easy. It is tempting to imagine extinction as a reset button, but in truth recovery is painstaking. It requires not just time, but chance, a lucky mutation, a favourable climate, an empty niche, and a creature curious enough to step into it. Every survivor must not only live, but adapt, diversify, and endure, and the world must allow it. And so, from the ash and the rot, and the whisper of spores, a new Earth emerged. In the next part of our journey, we'll step gently into the late Triassic, a world now more stable, more verdant, but looming just over the horizon is another collapse, another turning point, another extinction. But before we get there, let's rest here, just for a moment. The world is breathing again. Let's breathe with it. After the Great Dying, the world seemed determined not to make the same mistake twice. The Triassic period began as a time of renewal, hot, dry, and sparsely populated, but alive, very much alive. Life crept back across the land, across the reefless oceans, across the dust-blown plains of Pangaea. Survivors from the Permian took their cautious steps forward. Small amphibians reappeared near quiet ponds. Reptiles spread into a wide variety of ecological roles, and in the shadowy corners of this slowly recovering world, two unlikely lineages began to stretch their limbs and test the wind. Early mammals and early dinosaurs. But Earth, vast and ancient as it was, had another roll of the dice planned, And this time, the change would come not from impact or freeze, but from deep within again. Another great upwelling, another flood of fire, roughly 201 million years ago at the very end of the Triassic period. The world was once again destabilized by immense volcanic activity. A region known to geologists as the Central Atlantic Magmatic Province, or CAMP, began to split the supercontinent apart. What was once a single landmass began to crack. Lava spilled into these fissures, spreading across what would eventually become parts of modern-day North and South America, Europe and Africa. These eruptions were not dramatic in the short term. They didn't send ash into the stratosphere in a single blast, but they were relentless. For hundreds of thousands of years, pulse after pulse of volcanic activity released staggering amounts of carbon dioxide into the atmosphere. With the added CO2 came global warming. Again. But this time, the process was laced with chaos. Temperature swings, acid rain, ocean acidification and hypoxia unravelled many of the ecosystems that had only just begun to recover. Amphibians, so sensitive to environmental change, were hit especially hard. Large reptiles that had ruled the Triassic deserts, some slow, some armoured, some massive, began to disappear. The ocean's chemistry shifted. Marine life experienced a turnover. Certain species of ammonoids and conodonts vanished. Coral reefs, just beginning to reform in the late Triassic, suffered a major setback. In some places, entire marine food webs collapsed again, like a tower rebuilt too soon on unsteady ground. And yet, as always, change brings opportunity. With the old guard fading, new creatures moved into the void. Among them were the early dinosaurs, still small, still relatively rare, but quick, lot-footed, efficient in movement and metabolism. Unlike many of the larger reptiles that had dominated before, dinosaurs seemed better adapted to the volatile climates of the early Jurassic that followed the extinction. They were upright walkers, with hips that allowed greater stamina. Some were carnivores, like Caelophysis, a narrow-snouted predator that hunted in packs. Others, like Plateosaurus, grazed on tough plant matter, using their long necks to reach higher than most competitors. This moment, quiet and largely invisible in the fossil record, marks the dawn of dinosaur dominance, not because dinosaurs suddenly evolved superior traits in response to the extinction, but because they were already there, quietly coexisting in the background. The volcanic crisis simply cleared the stage. There's something poetic about this, something that whispers softly through the layers of time. Evolution doesn't favour the flashiest. It favours the ready, the adaptable, the ones waiting in the wings, unnoticed, until the world changes in just the right way. The early mammals, too, were present. Tiny, likely nocturnal, warm-blooded and insectivorous. They skittered through underbrush, built burrows, and lived in the shadows of the larger reptiles. For now they remained in the background, but they were learning, watching, surviving. Geologically, the Central Atlantic Magmatic Province played a key role not just in extinction, but in shaping Earth's geography. It began the breakup of Pangaea, slowly opening what would become the Atlantic Ocean. As the land masses drifted apart, new coastlines formed, new ecosystems, new migration routes. The Earth, once a single great continent surrounded by ocean, was becoming a more complex patchwork, a world of islands, peninsulas, inland seas. In this shattered balance, life did not falter. It shifted. What we learned from this extinction, smaller than the one before, but still one of the 5 great events, is that stability is temporary, that the forces which tear apart continents and boil oceans also open new spaces. That destruction is not the end of the story, but the next paragraph. And so, the dinosaurs rose, not in conquest, but in absence. The world they inherited was not the one they had been born into. It had changed under their feet, and they simply stepped forward. As we leave the Triassic and enter the Jurassic, picture a landscape beginning to heal again, volcanoes cooling, skies clearing, strange new forests pushing upward toward the sun, and walking through them, tall, curious, alert. A creature with a long tail, feathered arms, and eyes that watched the world not with fear, but with possibility. The Earth was giving evolution another chance, and this time it would take the shape of giants. With the chaos of the Triassic fading into the distance and the world's volcanic fever beginning to cool, the Jurassic period dawned quietly, like morning after a storm. The continents, now drifting apart into slowly forming shapes we might one day recognise, were edged by warm, shallow seas. The skies were wider, the forests were taller, and walking through them came creatures that, for the first time in Earth's history, could truly be called giants. This was the age when dinosaurs stepped confidently into the centre of the evolutionary stage. They arrived not in a hurry, but with the calm of a lineage that had time on its side. From their early, wiry ancestors, dinosaurs diversified into dozens of forms, some quick and graceful, others massive and deliberate. The sauropods, with their long necks and even longer tails, towered over ancient landscapes like living cranes, pulling leaves from the canopy with soft lips and thick tongues. Creatures like Brachiosaurus and Diplodocus roamed in herds across fern meadows and open plains, their sheer size discouraging predators before a single step was taken. On the other side of the spectrum, theropods evolved into nimble carnivores. Allosaurus, with its deep-set eyes and blade-like teeth, hunted across floodplains, while smaller coelurosaurs darted between trees, feathers beginning to fringe their limbs like forgotten shadows of a future yet to arrive. These early feathers weren't for flight, at least not yet, but perhaps for warmth, for display, for sensing the world in new ways. The Jurassic was in many ways a period of stability. After the shocks of the Permian and the flare of the Triassic, life began to settle into new rhythms. The Earth was warm and lush. There were no polar ice caps, rain fell often, and vegetation grew thick across most continents. Giant conifers, cycads, and ginkgos formed dense forests, while ferns blanketed the understory. This botanical abundance fueled the rise of herbivorous dinosaurs, who in turn shaped the very landscapes they grazed. In the oceans, life had also rebounded and reimagined itself. The reefs, once dominated by sponges and microbes, now belonged increasingly to scleractinian corals, whose descendants would form today's vibrant coral systems. Marine reptiles returned to the waves in sleek hydrodynamic forms. Ichthyosaurs, built like dolphins, plesiosaurs with long necks and paddle limbs, plesiosaurs with wide jaws and crushing bites. Cephalopods, particularly ammonites, spiraled back into dominance, their beautiful coiled shells once again common in shallow marine sediments. Fish diversified, crustaceans scuttled along reefs. The seas were alive with motion, colour and complexity. And above all of this, something stirred in the skies. The first true birds were not quite the delicate flyers we know today, but they were learning. Creatures like Archaeopteryx, preserved in fine Bavarian limestone, show us feathered wings, clawed fingers, and a toothed beak. They were caught between two worlds, air and land, reptile and bird, and in them we glimpse not just a moment in evolution, but a sense of possibility. That something as radical as flight could emerge from a lineage born of earthbound hunters. Insects buzzed and flourished as well. Beetles and dragonflies were common, feeding on decaying plants and smaller creatures. The first social insects may have begun experimenting with communal behaviour in this time, though it would be millions of years before true ant colonies marched in rows. And mammals, still small, still nocturnal, still living in the edges, but diversifying slowly into forms that would one day echo the larger shapes of the world they inhabited. Gliders, burrowers, climbers, diggers. In the dinosaur shadow they refined themselves with patience. This era didn't lack tension, but the disasters that punctuated it were regional. not global. A volcanic flare here, a sea level change there. But nothing yet that would shake the tree of life from its new high branches. And so Earth, for a time, grew quiet in its ambition and wide in its reach. This balance wasn't permanent, of course. No era is. But for tens of millions of years, the Jurassic offered something that had eluded Earth for a long time. Room. Room for life to spread, to specialize, to take risks. And in that space, evolution danced. The ecosystems of this time were complex and deeply interdependent. Dinosaurs shaped the vegetation through browsing and trampling. Plants responded with new growth strategies, new heights, new defenses. Carnivores hunted in coordinated pairs or competed across territories. Flight was being tested. Swimming had been mastered. Burrowing was underway. The biosphere was singing in full harmony. And in the silence between disasters, greatness grew. As we drift from this session to the next, hold the image of a Jurassic morning, steam rising from a warm forest floor, the slow creak of a sauropod lifting its head into sun-dappled branches, the rustle of feathers in the canopy, the quiet splash of a marine reptile slipping into deeper water. Nothing is urgent, nothing is forced, but deep in space a rock is waiting, and far in the future the sky will fall. It begins with a shadow that moves far too fast, cast not by clouds or wings, but by a visitor from the outermost reaches of the solar system. A rock, perhaps 10 kilometers wide, spinning silently through the void, indifferent to what waits below. It carries no malice, no intention, but its path is certain, and when it meets the Earth, it will change everything. The Cretaceous-Paleogene extinction, also known as the K-Page event, was sudden, violent, and absolute. Unlike the slow-motion devastation of the Permian or the drawn-out unravelling of the Devonian, this extinction occurred in a flash, geologically speaking. In the span of what may have been hours, days, or at most a few years, entire ecosystems were obliterated. Dinosaurs, who had ruled the land for over 160 million years, vanished. So too did the ammonites that filled the seas, the flying pterosaurs, the marine reptiles, and untold numbers of microscopic species at the base of the food chain. The world didn't just lose species, it lost its balance, its rhythm, its voice. The story begins, at least as we now understand it, with a collision. The Chicxulub impactor, named after the region in Mexico where the crater lies buried beneath rock and time, slammed into what was then a shallow sea near the Yucatan Peninsula. Travelling at more than 70,000 kilometers per hour, the object struck with a force estimated to be over 1 billion times more powerful than the atomic bombs dropped in World War II. In an instant, Earth's surface buckled, rock vaporized, a fireball expanded outward, igniting everything in its path. Forests burst into flames thousands of kilometers from the point of impact. Shockwaves circled the globe. Earthquakes were triggered on every continent. But perhaps the most devastating effect was what rose into the sky. Dust, soot, sulfates. Tiny particles launched so high and in such quantity that they shrouded the planet in darkness. Photosynthesis stopped. Plants withered. The herbivores that relied on them starved. The carnivores that relied on them in turn fell. Food chains collapsed like bridges pulled from their centre. Ocean plankton populations crashed, causing cascading extinctions in marine environments. Temperatures plummeted. A global winter set in. Cold not because of ice, but because the sun itself had been hidden behind a curtain of ash. In some places, the first day may have been the last. In others, it may have taken months or even years for extinction to complete its sweep. But the result was the same, an abrupt and unforgiving reset. Approximately 75% of all species on Earth disappeared. The dinosaurs, so long the dominant force on land, were particularly vulnerable. Large-bodied, specialised and heavily integrated into their ecosystems, they found no foothold in this new world. Their bones lie in silence now, scattered across every continent, some still posed in the moment they fell. And yet, once again, not everything vanished. In the underbrush, small mammals survived. In the branches, some feathered dinosaurs, those we now call birds, found ways to adapt. Crocodilians endured as they had through earlier extinctions content in their watery domains. Seeds lay dormant. Spores waited. Fungi returned, feasting again on the dead. It is difficult to imagine the emotional weight of this moment, even knowing it occurred 66 million years ago. The silence afterward would have been profound. A world without song. No buzzing of insects. No flapping of pterosaur wings. No crashing of titanosaurs through jungle canopies. Only ash. Only stillness. Only the soft reshuffling of evolution's deck. The Cretaceous was a time of abundance, of flowering plants, diverse dinosaurs and vibrant ocean life. It ended not because of failure, but because of fate. The Earth had been struck by chance, and that chance reshaped the trajectory of life. There is a strange mercy in how quickly it happened. The planet did not suffer through slow decline. Instead, it passed through a door, and emerged on the other side as something new. But it is also a sobering reminder. We often think of life as resilient, and it is. But it is also fragile. A single rock from space, no matter how ancient or distant its origin, can erase millions of years of progress in a moment. But this is not the end of the story. It is the pause. Because life, cloaked in fur, curled in burrows, waiting in seeds and shells, was not finished. It never is. As we move to the next session, we won't look at the fire or the crater or the statistics. We'll look at the line, the thin band of iridium that tells us it all happened. A quiet scar in the rock that says, yes, there was a day the sky fell. And yet, here we are. If you could peel back the surface of the earth like pages in a book, you would eventually arrive at a thin, dark seam. A narrow layer, no thicker than a coin, pressed between two chapters of rock. Above it, fossils of mammals, birds, flowering plants. A world that feels familiar. Below it, ammonites, towering dinosaurs, palm-like cycads, and things that no longer walk this world. And between them, this razor-thin, silent mark is time's punctuation. The line that separates a vanished world from the one that followed. A whisper of violence preserved in stone. This is the iridium layer. It is not grand to look at. In many outcrops around the world, it appears as nothing more than a smudge of clay with slightly unusual chemistry. But its story is vast. Because this layer, found in sedimentary deposits from Italy to New Zealand to North America, contains unusually high amounts of iridium, a dense silvery metal that is rare on Earth's surface, but relatively common in asteroids and meteorites. Its presence in this global layer is one of the strongest pieces of evidence that the Chicxulub impact was not a local catastrophe, but a planetary one. The discovery began quietly, as many scientific revelations do. In the 1980s, Luis and Walter Alvarez, a father and son team, a physicist and a geologist, were studying limestone formations in Italy when they noticed the spike in iridium. It was too high to be explained by volcanic activity alone. Other sites showed the same pattern, and all these deposits sat precisely at the Cretaceous-Paleogene boundary, the line where the fossils of dinosaurs abruptly stopped. They proposed the unthinkable, that a massive asteroid impact, not slow climate change or long-term volcanism, was the cause of the extinction. It was a bold claim. At the time, it bordered on heresy in paleontological circles. But as more evidence accumulated, shocked quartz, formed under high-pressure impacts, microtectites, tiny glass beads thrown out from molten rock, a buried crater in Mexico. The pieces began to fit, and so the story of the dinosaur's end gained its fingerprint. The iridium layer is a time capsule, not just because it holds evidence of impact, but because of what it doesn't contain. Below it, the diversity of life is wide and rich. Above it, for a brief moment in geologic time, there is quiet, a loss, a pause. Geologists sometimes speak of this boundary as a mass extinction horizon, and the term is apt. Not a slope, not a decline, but a horizon, sharp, abrupt, like a door slammed shut, and on the other side, a world that must learn to breathe again. There is something strangely comforting in this ability to read history in rock, to place your hand on a cliff face or a canyon wall and know, with quiet certainty, that this line tells a story, that something happened here, not just vaguely, but precisely. A day, a moment, a before and an after. In some places you can see it yourself. The famous Hell Creek Formation in North America, the Gubbio clay layer in Italy, and even remote sites in Antarctica, all carry the same signal. Iridium, quartz grains shattered by sudden force, fossils of ammonites just below, and the first mammals just above. The pattern is universal, and yet the layer itself is silent. It does not explain, it only records. The elegance of this boundary lies in its subtlety. There are no bones within it, no dramatic fossils, just dust, particles that drifted through a scorched sky and settled gently over a dying world. And now, millions of years later, they sit in quiet strata, waiting for eyes to notice. This is how Earth remembers, not in words, not in photographs, but in layers, in mineral traces, in isotopes, in ash and soot and grains of metal from beyond our planet. Our greatest stories are written not in ink, but in time. And though this particular layer marks an end, it also marks a beginning. Because what rose after it, slowly, cautiously, but steadily, was the age of mammals, of flowering plants, of forests teeming with birdsong and bees, of brains that would one day learn to split atoms, launch satellites, and read the secrets hidden in ancient rocks. The iridium layer is more than a geological curiosity. It is a mirror, a reminder of how fragile the world can be, and how enduring. That something as small as dust scattered across the world in the wake of a single terrible moment could one day guide us to understanding. So the next time you find yourself walking near a cliff, or running your fingers across a polished slab of stone in a museum, imagine what lies within. Not just time, but memory. A quiet archive of everything Earth has endured and survived. Because after all the fire, all the freezing, all the silence, we're still here, and so is the story. After the silence, a whisper. After the ash, a breath. The age that followed the Cretaceous-Paleogene extinction was not triumphant. It did not open with great migrations or epic struggles for dominance. Instead, it began in the quiet corners, the hollows of tree trunks, the tunnels beneath the soil, the cool shadows where life had waited out the storm. There, in places the dinosaurs had overlooked, something stirred. Small, warm, soft-blooded, and persistent. Mammals, for so long background characters in the story of life, began to take slow, cautious steps into the foreground. They were not new. Mammals had been around for more than 100 million years by the time the asteroid fell. But in the world of the dinosaurs they had kept to the edges, mostly nocturnal, small-bodied, insect-eating creatures who tucked themselves into niches where they wouldn't be noticed. It was a strategy born of caution, and it worked. When the giants fell, the mammals were still there, waiting. The earliest post-extinction mammals were diverse not in size or shape, but in resilience. They could eat a variety of foods, seeds, insects, roots, even carrion. They reproduced quickly. They found shelter in burrows, under rocks, in dense vegetation, And perhaps most importantly, many of them were likely warm-blooded, able to regulate their internal temperature in a world that was still reeling from climatic chaos. As the skies cleared and plants returned, these small survivors began to evolve, not with haste, but with quiet determination. The Paleocene epoch, which began just after the extinction, saw forests regrow across much of the planet. Not the coniferous groves of the Jurassic, but flowering plants, angiosperms, that now spread rapidly, carpeting hillsides and valleys with colour and scent. These plants produced fruit and nectar, opening new ecological opportunities for animals that could climb, forage, or hover. Insects followed. Bees and butterflies evolved alongside the flowers, creating new feedback loops of pollination and adaptation. And the mammals, always watching, always learning, began to diversify in response. From a few modest forms arose the roots of great lineages: primates, who would one day climb toward consciousness, ungulates, who would gallop across future grasslands, cetaceans, who would return to the sea and learn to sing. But none of that was visible yet, for now they were only seeds, curious body plans, shuffled genomes, quiet adaptations passing from parent to offspring. The world was not empty anymore. It was growing. It was humming again. In the oceans, fish recovered swiftly, and the corals began to build reefs again. In place of the great marine reptiles came whales and dolphins, though they would not emerge for tens of millions of years. For now, it was a time of realignment, of reshuffling the rules of life on Earth. Birds, the only dinosaurs to survive, diversified rapidly. Some grew small and colourful, flitting between flowering branches. Others, like Gastornis, were large and imposing, flightless giants who dominated the early post-dinosaur world like quiet sentinels. Every feathered wing beat, every reptilian hiss, was a continuation of a story that had nearly ended, but didn't. It's easy to think of the extinction as a dividing line: before, dinosaurs; after, mammals. But it's more subtle than that. The truth is, mammals and birds rose not because the dinosaurs failed, but because the conditions changed, and in those new conditions, cooler, more seasonal, with food scattered in different patterns, it was the adaptable, the fast reproducing, the small and flexible, who found footing. The mammals did not rush to dominate. They drifted upwards slowly, generation by generation, filling in the open spaces. The process took millions of years, but in the vast sweep of time, that's still quick. Nature had a void to fill, and life always leans into emptiness. By the Eocene, some 10 million years later, the forest teemed with early lemurs, tiny horse-like animals, and creatures with strange teeth and stranger diets. Evolution was no longer rebuilding the past, it was inventing the future. The Earth was not healed, not entirely. The climate was still unstable at times, and future ice ages loomed. But the biosphere had stabilized. The food webs had reformed. The planet, once so still, was vibrant again, and it had a new rhythm. One carried not by roars and stomps, but by paws in the underbrush, hooves in soft soil, wings slicing through air, and eventually, though no one could have known it then, by hands. The mammals did not replace the dinosaurs. They followed them. They inherited a world shaped by extinction and made it their own. As we reach the end of this journey, take a moment to breathe in the quiet that follows catastrophe. Not the silence of loss, but the hush of new beginnings. Life, like the tide, always returns, sometimes softer, sometimes stranger, but always, inevitably, forward. The next age had begun, and the world once again was listening. Mass extinctions at first glance appear to be stories of absolute endings. They are framed by loss, defined by absence, measured in vanished species and empty landscapes. But if we step back, if we take the longer view, what we see is not only destruction. What we begin to notice, quietly emerging from the fossil record is a pattern, one that weaves itself through time like a breath held and then slowly released. Extinction is not the end of a life, it is the reshaping of its possibilities. The history we've just walked through is marked by 5 great upheavals, each one swept clean a vast and complex world. Coral reefs collapsed, forests burned to their roots, sky and sea emptied, entire evolutionary lineages, some of which had endured for hundreds of millions of years, simply blinked out, leaving behind no descendants, only impressions in stone. But then, in the aftermath, something remarkable happened. Every time. The Earth did not stay quiet. It didn't remain barren. Instead, from the fragments, from the overlooked, from the edge dwellers and soil clingers and air hiders, life reassembled itself, not into copies of what had come before, but into something new. Extinction, then, is not just a subtraction. It is a space, a clearing in the forest of evolution. And nature, like any good storyteller, never leaves a blank page for long. Take the Permian extinction. In its wake, new reptiles emerged, ecosystems were rebuilt from microbial mats upward, and eventually, the age of dinosaurs began. After the dinosaurs fell, birds and mammals diversified, flowering plants exploded into complexity, and the age of mammals took shape. Each great loss carved the path for great novelty. But these transitions were not instantaneous, nor were they easy. Evolution is not a graceful dance. It is a slow, stumbling reach, and the species that emerge are not always the strongest, or the cleverest, or the largest. They are simply the ones best suited to a changed world. That's what extinction teaches us. Not just about biology, but about time itself. Time, on Earth, is not a straight road. It bends and loops. It collapses and resets. What seems permanent one moment becomes ancient history the next. And through it all, life is rewriting its script, adapting to new climates, new pressures, new chances. In a way, mass extinctions are like punctuation marks in the story of life. They are the deep pauses, the moments where the narrative hesitates, inhales, and shifts direction. Without them, Earth's biosphere might have remained static, crowded with familiar forms, comfortable but unchanging. Instead, we got feathers, we got flowers, we got flight. Even human beings, our intelligence, our tools, our cities, are part of a lineage that emerged not in stability but in aftermath. Our story exists because others ended. That doesn't make extinction beautiful, but it does make it meaningful, and it reminds us of something else. Fragility is not the opposite of strength. Fragility is what makes transformation possible. What breaks can be reshaped. What ends can be rewritten. Earth is old. It has seen things we can barely imagine. For most of its history, it has been home to creatures and systems that no longer exist. But it has also been a stage for rebirth, again and again. That too is part of the story. And so, when we talk about extinction, not just in past tense but as something ongoing, we are not speaking only of loss. We are speaking of change, of what is at stake, of what could come next. In this session, we pause not to mourn, but to reflect. Extinction matters because life matters, because time is not infinite for any one species, but it is generous with possibility. Because even in the wake of ruin, the planet offers a canvas, and evolution, with its patient brush, begins again. As we drift into the next session, we'll zoom in. We'll look more closely at the creatures who made it through, the unremarkable ones, the quiet ones, the ones who remind us that sometimes the future belongs not to those who roar, but to those who endure. Because even after the world ends, life does not wait for applause. It simply begins again. In the towering dramas of deep time, it is tempting to focus on the loudest characters. The thunder-limbed dinosaurs, the armoured sea creatures, the soaring reptiles that once filled the skies. But those were the visible ones, the spectacular chapters. When we look closer, through the microscope and the sediment, we find another cast entirely, one composed of quiet survivors. Creatures and life forms that did not dominate but endured. They are not the heroes of extinction stories, yet somehow they are always still there when the page turns. Take Lystrosaurus, for instance. A barrel-chested, tusked synapsid with a slightly comical face and a gait like a determined toddler, Lystrosaurus lived through the worst extinction event in Earth's history, the Permian-Triassic catastrophe, when nearly 90% of marine species and 70% of terrestrial vertebrates vanished. This odd little animal managed not only to survive, but to thrive. In some fossil beds, up to 90% of all vertebrate remains come from Lystrosaurus. What made it so successful? Not size, not speed, but adaptability. It lived in burrows, could tolerate low oxygen environments, and had a flexible plant-based diet. It wasn't specialised, it was persistent. In the shattered silence after the Great Dying, when the world was darkened by volcanic ash and soil had barely begun to recover, Lystrosaurus snuffled through the dust and pressed on. Creatures like this that tell us something profound. The future often belongs to the unassuming. Consider the ferns, ancient plants older than flowering species, older than conifers, older even than most insects. They reproduce by spores, not seeds, and yet they have weathered all 5 mass extinctions. After each catastrophe, fossil records often show a sudden spike in fern spores, a phenomenon known as a fern spike. It's as if the moment the fires burn out and the ash cools, ferns are already uncurling their fronds, ready to begin again. They don't grow fast, they don't climb high, but they are resilient in the truest sense, quiet, efficient, and stubbornly rooted in time. Then there are the microbes, the invisible majority. They were here long before trilobites, before oxygen, before even the moon settled into orbit, and they have never left. In the boiling vents of oceanic rifts, in the frozen soils of Antarctica, in the radioactive waste of uranium mines, microbes carry on. Some are extremophiles, thriving in conditions where no complex organism could survive. Places too hot, too salty, too acidic, too dark. During mass extinctions, while ecosystems collapsed and surface life faltered, these microscopic beings continued their endless chemistry. They broke down the dead, recycled nutrients, maintained the planet's invisible balances. Without them, recovery wouldn't begin. They were, and remain, the caretakers of the biosphere. And then, of course, there are the mosses, clinging to rocks, thriving in cracks, soaking in moisture from the gentlest of mists. Mosses are a lesson in patience. They've survived ice ages and asteroid winters. They don't tower like trees or bloom like roses, but they soften the world. They colonise bare stone and make it habitable for other life. They are among the first to return after devastation, like a green breath across scorched earth. When we think of survival, we often picture power, claws, armour, cunning. But the true masters of endurance are those who require little, who move slowly, who go unnoticed. It's not just about biology, it's about philosophy. There's something deeply reassuring in the idea that survival doesn't always favour the fastest or strongest, that sometimes it's the steady, the overlooked, the humble that persist, the fern that doesn't mind shade, the microbe that thrives in the dark, the Lystrosaurus that waddles forward when others fall. We live in a time where noise is everywhere, online, in cities, in daily life. But evolution tells us that silence has a power of its own, that endurance is not always loud, that resilience is often built from slowness, from flexibility, from the ability to bend without breaking. These quiet survivors, scattered across time and taxonomy, offer a gentle kind of hope, because they remind us that catastrophe is survivable, and that life, even at its smallest, carries the spark of continuity. If the giants fall, something else will rise. If the forest burns, something green will return. And in the soil, in the shadows, beneath the ash and the stillness, something always waits. In the next session, we'll softly step into the present. Not to sound an alarm, but to listen. Because some scientists believe we're living through another extinction right now. Not one caused by meteors or volcanoes, but by us. But for now, let the moss be moss. Let the microbes do their ancient work. Let Lystrosaurus rest, fossilized and remembered as a symbol of life's quiet determination. Because sometimes the world is saved not by heroes, but by those who simply hold on. The Earth is quiet now, at least from a cosmic perspective. No asteroids loom large in the sky. No supervolcano rumbles underfoot. The continents drift with a patience that could lull you to sleep. On the surface, all seems well. But when scientists tilt their ears toward the biosphere, when they examine the data hidden in satellite imagery, population records and habitat maps, a different rhythm emerges, one more urgent, though barely audible. Not a shout, not even a cry. A whisper, a soft, persistent unravelling. Some believe we are living through the beginning of a sixth mass extinction. This time there is no celestial rock, no cascade of lava. The agents of change are subtler, spread out across countless decisions, economies and systems. We pave forests to build roads. We fragment habitats to make room for crops. We alter the chemistry of the atmosphere with invisible gases. Each act on its own is small, but together they move with the same weight as tectonics. Species are disappearing at rates far above the background level. Amphibians, with their delicate skin and sensitive metabolisms, are vanishing in silence. Pollinators decline, unnoticed, until the flowers begin to miss them. Coral reefs bleach not in fire, but in sunlight too warm for too long. It is not a bang, it is a fading. But this isn't a lecture, it's a reflection. Because the lesson of Earth's past is not just that life has ended, but that it has adapted. And even now, many species are adjusting. Some birds change their migratory paths. Urban foxes and raccoons learn to navigate city alleys and crossing signals. Insects evolve resistance to pesticides faster than we can name the chemicals. Still, it is a fragile balance. There's something almost sacred about knowing we are part of the same story as Lystrosaurus and the trilobites, as the ammonites and the early mammals. The same planet, the same cycles of light and dark, of cold and warmth. And now we hold a pen, not the only one, but a powerful one, capable of writing what comes next. The potential for a sixth extinction is not written in stone. It is written in choice. We can decide what kind of chapter this becomes. We can reforest, rewild, protect, restore. We can study the past not just to marvel at it, but to learn from it, to understand the signals, the drop in biodiversity, the shifting of climates, the collapse of food chains, and respond while there is still time. Unlike in the past, we have the ability to see it coming. We can read the layers before they harden. And that is something astonishing. But we must be gentle, gentle with our landscapes, gentle with the creatures who share this home, and perhaps most importantly, gentle with ourselves, because the burden of knowing can be heavy. It can make us feel powerless or overwhelmed or lost. But the lesson of extinction is not despair. It is perspective. The Earth has recovered before. It will again. But the shape it takes afterward, the creatures it carries forward, the dreams it shelters, will be different. The sixth extinction, if it unfolds fully, will not mean the end of life. But it may mean the end of the world as we know it. And still, the whisper is not yet a scream. There is still time to listen, time to breathe with the planet rather than against it, time to ask not what must be sacrificed but what can be preserved, time to step carefully. In this age, where the agents of extinction wear human faces, we also have something no previous era had, consciousness, A species that can reflect, can imagine futures, can feel empathy not just for its own kind, but for mosses and microbes and coral polyps and Arctic foxes. This is new, this is rare, and that means our story doesn't have to echo the others. Perhaps this extinction can be interrupted. Perhaps instead of a black line in the fossil record, we'll leave behind a softer mark, one that says, "Here they paused, and chose a different way." Let that be our hope. In the final session, we'll look once more at what life does best. Not just survive, but adapt, rebuild, return. Because even if we walk through fire, through flood, through silence, life still leans toward the light, and so can we. The story of life on Earth is not a single sweeping epic. It is a mosaic, millions of stories, layered and fractured, lost and rediscovered. Some are told in stone, others in DNA, and many more still drift in the silent dark, forgotten but never entirely erased. But if there is one through line, one thread that holds across every extinction, every emergence, every age, it is this: life returns. Even when it looks impossible. Even when the oceans are anoxic, when the sky is dimmed with soot, when the forests have turned to ash, and the reefs are gone. Somehow, somewhere, something endures. In the aftermath of every mass extinction, the world did not become empty. It became different. Coral reefs reappeared, built from new architects. Plants climbed upward again, from moss to fern to tree. New animals explored old places with new limbs, new lungs, new dreams. And the earth, though scarred, carried them forward. After the Permian extinction, the worst in history, came the rise of dinosaurs. After the asteroid impact that ended the Cretaceous, came birdsong in forests and mammals stirring in leaf-littered silence. Even now we see it in small things. A single blade of grass cracking through concrete, lichen colonizing bare rock, a coral polyp settling on the remnants of a bleached reef and beginning, cautiously, to build again. The instinct to continue is not glamorous. It is not loud, but it is astonishing. Because survival is not just about holding on. It is about reshaping, adapting, taking the conditions that remain, however imperfect, and making them enough. Life does not wait for perfect environments. It makes do. It improvises. It persists. And perhaps so do we. When we feel overwhelmed by the scale of things, by the weight of time, by the threats we face, by the complexity of ecosystems and climate and extinction, it helps to remember how much has already changed, how many endings the Earth has known, and how many beginnings it has made from them. You too are part of that legacy. You are the product of survivors, of ancient fish who crawled onto land, of mammals who tucked themselves into burrows while fire rained from the sky, of primates who adapted to shifting forests, who reached for fruit and language and tools. You carry the echo of every extinction inside you, and every renewal. You are proof that the story continues. So what does it mean to be here, now, in a time of whispers and warnings? It means you are living in a turning chapter, not the end, not yet, but a moment where the next part hasn't been written, a moment of agency, of possibility. If the Earth has taught us anything, it is that healing is slow but real, that the world can fall silent and still find its voice again, that the cracks don't end the story, they are where the green begins. And so, in this quiet hour, as we look back over oceans of time and fields of vanished forms, what remains is not just the memory of what was lost, but the astonishment of what returned. Life is a quiet genius. It doesn't need permission. It doesn't ask to be noticed. It just grows. It just continues, and that is enough. So tonight, sleep softly with the knowledge that you're part of something old, vast, and deeply resilient. You are one note in the Song of Earth, long, layered, sometimes shaken, but never truly silenced. Whether you're surrounded by city lights or forest stillness, whether you feel heavy with thought or light with rest, know this: the world has ended before, and it has always begun again.